Okay, problem number 2. The intensity of light in the Caribbean apparently diminishes 15% every 3 meters as it enters the water. Caribbean would be nice about now. So here we go. Here comes the light. And as the light goes down into the water every 3 feet, so the intensity is going to go down 15%. So we're going to start 100% obviously at the surface. We go down 3 feet, it's going to be down to 85%. We go down 3 feet again, and it's going to not be at 70% of the original. It's going to be at 15% of the 85% that it was at 3 feet. So it's going to be 15% of the remaining light, and then 15% of that remaining light, and then 15% of that remaining light. So for all practical purposes, you could say that the light is never fully going to diminish, and yet practically speaking there will be a point where you're not going to be able to see the light from the surface. So probably somewhere down in the very small percentages, the light is this function is going to not work anymore. So here we go. Let's start off, and they're asking us to calculate a exponential function in terms of the intensity, so whatever that intensity is at the start, and the depth of the light into the water. So here we go. We'll set the initial intensity as our variable I0, which will be the surface intensity when it's at 100%. So that's a nice thing to have right there. So here we go. We have our surface, our initial intensity here, and we're going to set up a standard exponential function. So the intensity, which is related to the depth, is going to be the initial intensity times some base b raised to the depth. And so as the depth increases, the intensity is essentially going to decrease here. So here we go. We're going to just then start off, and they say that since the intensity is dropping by 15%, we have two data points. We have the initial, and we have the data point of at 3 feet, which will be at 85% of the initial. So if we plug in 3 for the d, we could say that I of 3 equals 85% of the initial, but the initial at 0 depth, or our just initial value. Now b to the 0 is just what? 1. That's right. So I3 is 0.85 of I0, and that's going to be our starting point here as we begin to look at how to calculate. So I have two data points, and what I can do is, if I take I0 of 3 equals 85% of the initial, then I can divide that data point by the first data point and solve for the unknown b. Now you're going to have, at this point, we have 3 unknowns in our equation. We have the intensity amount, we have the depth, and we have this multiplier, this base. So here we go. I'm going to take the 85% I0 equals IOB3. So that's plugging in 3 for the d there, and that's a known value here. So then I'm going to divide that by the initial value, which equals I0 of B0. Now I have some things that will cancel nicely. So I can cancel out the IOs on that side. I can also cancel out the IOs on that side, which then just leaves me with a simple equation of 0.85 equals b to the third. Well, to solve for this one, I just take the cube root, or the third root of both sides, and I end up with 0.85 to the 1/3 power equals b. Now that's just a number, and if I wanted to take and solve and put that in as a decimal, then I would get that decimal right there, 0.94727, or some kind of rounding in there, is the same as 0.85 to the third, or the cube root of 0.85. So if you want to mess around with that in your calculator, you can do that. Take the cube root of 0.85. Some of you have that button on your calculator. So if I take that number right there for the b value, then that's going to give me a little formula here of I-O times 0.85 to the 1/3 d, or I-O 0.94727 to the d. And that's our equation, that's our exponential equation for the intensity of the light as it increases based on the depth and the initial intensity. Alright, so the second part then says we need to see when or where, at what depth, will the initial intensity be at 1% of its original intensity. So we're going to lose 99% of the initial intensity and just be down to 0.01 or 1% of the original intensity. So here we go. 1% I-O is the same as 0.01 I-O, which if I set that equal to our equation from the last page, I-O times 0.94727, raise that to a particular d. Now I can cancel some things out here. The I-O's are going to cancel, and then that's just going to leave me with 0.01 equals 0.94727 to the d. Well, this is where the logarithmic skills from the first problem have to come in, and we're going to take the natural log of both sides. I'm going to take the natural log of 0.01 equals natural log 0.94727 to the d. Well, natural log of 0.94727 to the d is just going to be d times the natural log of that number. So if I divide that over here, 0.94727 equals the d, then I end up with a d value of 85 meters. Okay, so at 85 meters down, you got 1% of the light left that was present on the surface. Alright, pretty simple. Alright, here we go. Practice exercise. We're going to try another one. We're going to say, what is the percentage decrease? So we're looking for how much is left, and then subtract that from 100%. So what is the percent decrease at 50 meters of depth? Obviously there's something left, because we know that at 85%, or at 85 meters, there is 1% left, so it's going to be something greater than 1%, and 1% left would be a 99% decrease. So I want you to go ahead and calculate what would be the percent decrease at 50 meters. Alright, I'll let you guys tackle that one, and we'll see you on problem number 3.